Hello students, welcome to the IMS Gate Academy. So as part of the Gate Score Booster session, we'll continue the second part of the computer organization architecture. One session we have already taken on COA under this Gate Score Booster session, in which so 2 or 3 chapters still memory management I have covered it. So those who are not watched, you can go to the one of the session with the last week I have taken. Okay. So just before going to this, just starting the session, just confirm all of you. So I hope my voice and the video part, everything is clear. Okay. So let's start the session. Okay. In which, so remaining part of this COA I'll be discussing through questions only. The ultimate agenda of this Gate Score Booster session is to understand, uh, it's kind of revision. So we are discussing the concepts and through what? Through question solving. Like some of the questions I taken from this chapter, like especially instruction pipeline, instruction format, addressing modes, as well as DMA controller, through which we will try to revise the topics. So during this one, if you have any doubts or there any kind of discussion you want to do it, just definitely you can comment it. We'll address that part also. Right. Okay. So what I'll be covering under this one? Under this one, majorly focus on the major focus on one is instruction pipelining, instruction pipeline based questions, instruction pipelining. So mainly you understand this, as well as instruction format also, instruction format, and also your addressing modes, addressing modes. Okay, this is one aspect. The second aspect is you understand DMA controller, mainly DMA controller. Okay, this is a IO part, you understand now, IO organization. Okay, in a previous session, like floating point number representation, the followed by memory hierarchy, main memory, like address map, cache memory address mapping techniques, those things we have covered in the last session. So try to cover that session also after this. So one of the important and most important topic from this one is this instruction pipelining, as well as instruction format also we can see it. So every year we can see one question from instruction pipelining. Okay. Let's take the question. Let's take the question now. A processor uses, the question you can read it. A processor uses fixed length 4-byte instruction and PC relative branching. A program segment contains 16 consecutive instructions placed in memory, starting address given, like hexadecimal address given. The memory is byte addressable memory. So now the I2 is the conditional branch instruction with the unsigned byte offset field. The value is 24 is given decimal now. Offset value. I2 is a branch instruction whose offset value is contained 24. The branch target instruction labeled by XST is a target instruction, basically you understand now. So what is the index value of the target instruction XST is asking now. Okay. Try it out, all of you. Try. You can take 1 minute time. Try to solve this question. Try to solve this question. Yes, those who are watching, try it out, attempt it. Program as, so I'm saying that program has 12 instructions, right? Program has 12 instructions are there now. Program has 12 instructions, like take. So instruction 1, instruction 2, instruction 3, 16 instructions are there. Sorry, a program segment contains 16 consecutive instructions are there. Like this, instruction like this. So instruction 16 like this. So this is a program content now. So I2 is a branch instruction, understand now. Its target somewhere will be there. We don't know target. Somewhere target is there now. Okay, target is there now. Now in this branch instruction, this offset value, branch followed by offset values 24 is given now. This is a instruction to like this, understand. Instruction to format, if you could see, opcode followed by, this is opcode, right? Opcode followed by this operand field is nothing but offset value is there now. Offset is 24 is given now. I3 is the next sequential instruction, I4 like this, last instruction I16 is there now. Whose target somewhere we don't know. He asking this address of the target instruction, index value of the target instruction. No? What is the index of the target instruction XST is asking now. The first of all I should understand the format of this instruction which is stored in a memory. So now if I take the scenario, so I'm just moving to here, sorry. Okay. If I take the scenario here, let's take memory. This is a memory, main memory. Okay, memory. So in the memory, you understand now. Somewhere address, starting address 0 only, right? Let me hexadecimal address given. I am taking 0 as a decimal address assumption now. So decimal address. From here, instruction 1 placed. So now a processor uses fixed length 4-byte instruction. Now instruction size is 4 byte. Each instruction size is 4 byte long. So I'll be writing this a 4 byte long now. So now second instruction starts from 4 only. Instruction I2 is a 4. It is also 4 byte long now. So now this 8 address start 4 to 7 is the I2 instruction. Now decimal address if I see I3 will start from 8. This also 4 byte long, correct? So like this somewhere my 16th address will be the 16th instruction now. Instruction 16th is there now. This is also 4 byte long now. What is this address in a decimal format if I see it? 16 into 4, right? So 64. Okay. The 0 to 64 nothing but what is this 64? This is 60. Okay, this is what 60. Isn't it? Am I right? All of you just confirm me. Those who are watching, just comment it. What is my question here? Address of the 16th instruction, is it 60 or not? Confirm me. Everyone. So like as is given address, 0th location onwards is given like 32 bit. Like 1, 2, 3, 4, 5, 6, 7, 8. 8 into 4, so 32. 32 bit address hexadecimal. But I am writing in a binary decimal. For the sake of simplicity, I written it just taken as decimal now. It won't change because 4 byte long, 4 byte 4, 8, 0, 4, 8, 16 like this I'll go. So 8, 12, 16 like this will go. Total number of instructions 16 into 4 is 64. Like last instruction is at 60 only. Correct. Now here this this IT instruction offset value is 24 is there now. 24 is there now. Now they are asking whose target instruction is what? They said IXST. What is index value of XST? Asking now. Simple. If I ask what is index value of I3? 8. What is index value of I2 is 4. What is index value of I1? 0. What is index value of I16? 60. Address of the instructional index is nothing but now. How to get the target address? So now simply you understand now. So branch instructions handled by use the PC relative addressing mode. I hope you might have studied PC relative addressing mode. Purpose of PC relative addressing mode to handle the branch type of instruction. What does mean? Example you understand now. The PC value initially is pointing to this 0 address. PC value initially pointing to 0 address means instruction 1. Once instruction 1, let's say I'm writing, no here I'm writing instruction 1 whose address is 0, right? 0. The PC is pointed here now. Once this instruction fetching is over, automatically PC is pointing to next instruction, that is I2. Correct or not? Again, when I2 instruction fetching is over, PC get incremented pointing to what? Next instruction I3, right? So I3 is there like this. It is pointed here now. I2 is what? Branch instruction, conditional branch. Condition is checked. Once condition is true, it has to jump to somewhere target instruction, right? Somewhere target instruction has to jump now. Meaning, it means that if instruction I2 completion over, after completion of instruction I2 branch instruction, if this condition is true, it should not run I3, it should run target instruction. In order to execute or in order to jump to the target instruction, PC value must be updated. So PC value right now is 80. This 80 has to change to this target value. So how changes happen? I'm saying you now understand now. So I'm saying now. So target, how to calculate the target address? How to calculate the target? So current PC value plus offset, simply you add it. Current PC value is what? 88. What is offset value? That is already stored, 24. So 24 plus 80, 8 is 32. Now see, it has to jump to what? 32. Wherever memory address present, 32. In a 32 position, whatever instruction is there, that we have to fetch it now. So answer for this question is that. So what is the answer now? Answer is 32. I hope it is clear, everyone. If anybody having a doubt related to this, just comment it. Yes. Target equal to current PC plus offset. Exactly true. Exactly true. So answer is right. The answer for this question 32 is right. Sheila Kumari. Yes. Yes. So these types of questions we have seen. One of the previous year gate question, he asked it offset value. He is given a target instruction also. Current PC value easily we can able to evaluate. So target value is given. He asked what is offset value in terms of instructions only given now. I hope this is clear. Okay. So now just before going to another question. So you have a doubt, right? Let me go back. Okay. So I repeat, a program segment has 16 instructions are there. Instruction number 2 is a branch instruction whose target is somewhere. The target of instruction name is XST. Okay. Every instruction size is 4 byte long is there. The program is stored from 0 address onwards in the memory in a consecutive manner they stored it. Now target instruction name is, what is target? I2 is a conditional branch instruction with unsigned offset value is given 24. The branch target instruction is what? XST. Now what is index value of XST is asking question now. Look at the program in the memory. In a memory, 0 address onwards, I1 is 0 position, I2 is at 4 because every instruction 4 byte long. I3 is what? I3 is what? 8, I4 like this, I4 will be 12. Like this keep if you go, my 16th instruction will be address at 60. Is it true? Yes, ma'am. Yes, ma'am. Is it true? The value is true. Instruction 16 is at address 60. Is it true? Just confirm me. Okay. Now I2 is a branch. I2 is a branch, right? I2 instruction is a branch, right? I2 now. How execution goes? I will take PC value which is pointing to I1, 0. First I will fetch I1 instruction. Once fetching is over, PC get incremented. PC will be pointed to I2. After execution of I1, I2 will start. After fetch of I2 instruction, PC automatically incremented pointed to instruction number 3. The address is what? 8. When during this branch execution time, if the condition is true, it has to jump to target instruction, which we do not know where to jump now. You're asking index value of address only, right? Assuming that a situation, there is a conditional branch instruction, we have to jump to target only, means a condition is satisfied now. If the condition is satisfied, we should not run instruction I3, we should run target instructions wherever it present now. To run the target instruction, my PC value should point it to the target address only, right? Isn't it? Now, the PC content must be updated. How to update the PC content? So, to solve this problem, PC relative addressing mode, we have to use it. What this PC relative addressing mode? Take simply current PC value. Look at the program instruction offset value, branch instruction offset value. Look at whatever value is there. Take that value, add to our current PC value. That's what simply I have taken. Current PC value 88 and offset is 24. Added become 32. Now 32 is the index of a target instruction that is going to fetch next cycle. So PC will become 8 after the fetch. Very good. I hope this solution is clear now. 32 is the right answer to fetch a target instruction. Name is what? XST. Is it clear? Confirm me. Similarly, we have taken already one session on COA in which floating point number representation, IEEE 754 format, cache addressing format, and also memory hierarchy, main memory. This all the aspects already I have taken. 2-hour session I have taken all. So it is available in the channel. So once after completion of this session, try to watch that also. It is going to really useful. Because last year I'm experienced, I'm telling last year similarly I have taken 2 sessions on COA. There were 1 or 2 questions were exactly matching, almost matching to the real GATE exam. I've seen it, especially CPU time calculation based question, and one more with respect to the memory hierarchy. That type of questions I've seen in the GATE paper 2025. It is, I did not say this one, the one of the students who watched in a YouTube only commented saying that, sir, this is something came. Chalo, we'll moving into other things. So now I'm just showing that we at IMS, we are offering the all-in-a mock test series. So in which these are the schedules, means the test are, some of the tests are already on live manner. So like your date wise, you can say total 12 mock tests we planned for the computer science and 6 mock tests for the data science paper. So those who are interested, definitely you can visit at this IMS Gate Academy, then you can purchase it. Okay. Sir, important questions only that can come, take that. Sir, important questions. See, the agenda of this sessions, some important areas. I'm choosing important, instead of important question, choosing important areas and some, what you can say, to get a clarity over these concepts, I'll be taking question through which solving these questions will get a clarity. That's the main idea of the sessions. I'll choosing important sessions, important topics on which some questions I framed it. Those questions I'm solving related to concepts also we can discuss it if doubts are there. So I hope this is clear. Okay. So next, so we'll move for the next question. So now IMS, we offer online classes also, fully online classes. Okay, in which main features if you see, the more than 800 teaching hours will be the live manner, also recorded form. So theory and exercise book questions are, booklet is given to you, so which contain almost 4,000 practice questions plus last 34 years question bank prepared with a detailed solution for each question, taking old paper questions also. So 1998 and so 99, 2000, those questions also solved it. And the main feature of the IMS is what? 12 mentorship sessions will get. The student can sit with the faculty, can take this own what you can say direction or preparation strategy for the any like upcoming exams. So now when it comes to tests, almost more than 130 tests are offering, including topic level, subject level, multi-subject and full length this one now. So moving into another question, it is very interesting question. Look at here. So I'll give it time, take the 2 minutes time, try to solve it. Try to solve this question now. Consider an hypothetical CPU whose instruction set support 3 address, 2 address, 1 address and 0 address instruction. The CPU uses fixed 24-bit instruction format. All memory addresses are word addressable and the system contains 128 word of memory. Each address field must be large enough to address the entire memory here. So this instruction set architecture contains 4 distinct 3 address instructions. Number of 1 address instruction is exactly 8 times the number of 3 address instruction. The number of 2 address instructions is exactly half of the number of 1 address instruction. The remaining opcode combinations are used for 0 address instructions. How many 0 address instructions can be encoded or designed for this architecture dash? It is instruction encoding also can tell. Instruction encoding also we can say. So now one particular architecture is supporting 3 types of addressing instruction. How many? 0, 1, 2, 3. 4 types are there now. 3 address, 2 address, 1 address, 0 address. 4 type of instructions. Okay, it is this operands are memory operands only. So memory size given 128 word memory now. And some category of instruction. How many instructions are there? Each category also given now. The rest is asking that how many 0 address instructions can be encoded or formulated from this architecture is the question. Attempt. Yes, 4 types of instructions are there. Try to solve. Yes. So instruction format, if you see the instruction format is this instruction, right? This instruction format is 24 bits long, right? 24-bit long is there like this. Okay. Now it is supporting, it supports this ISA. ISA supports 0 address, 1 address, 2 address, and what? 3 address instructions. 3 address instructions. Okay. Now, so one question, very simple question I'm asking. If 24 bits are there, how many just 0 address instruction possible? Can I say 2 power of 24 instruction possible or not? Suppose example, I'm asking simple. 2-bit number given to you. How many instructions, how many operands possible with the 2-bit number? 2 power of 2 we can write. 2 power of 2, 4 instruction possible. If I given 10 bits, how many instruction possible? 2 power of 10, 1024 instruction possible, sir. Like this 24-bit given to you, 24-bit 2 power 24 instruction possible. These 2 power 24 instructions are sum of naming. Let's take, I'm writing like something. Let's take, so I am just naming as. Did you read it? Like I repeat now, 24-bit instruction format is given to us, right? 24-bit instruction format given to us. Now all memory operands are word addressable, and address is given, address number of words in a memory is 128. ISA contain 4 distinct 3 address instructions. Number of 1 address instructions are exactly, number of 1 address instruction exactly 8 times of the number of 3 address instruction. Something given information now. I was saying that, so this instruction format, right? This instruction format. So this instruction set architecture of 24-bit long, right? 24-bit long. So this is supporting 0 address, 1 address, and 2 address, and 3 address instruction. Am I right? 0, 1, 2, 3 address instructions are there. Am I right, all of you? Just confirm me. Right. What was my question? 24-bit combinations. How many such instructions possible? 2 power of 24 is possible, right? 2 power of 24 possible now. This total 2 power 24 instructions are combination of the 4 types. What are the 4 types? Let's take example. I'm taking as something. I'm taking P. P is a 0 address. 0 address means no address will be there. So I'm taking the Q. Q is a 1 address. 1 address means I should add it 1 address field here now. Opcode. So now opcode. So Q is a 1 address. Opcode field Q into operand field. Now operand field, you understand, address field. 128 word memory is there. 7 bits required. So that I can write 2 power of 7. I can write P plus Q plus R. I'm writing. R is the 2 address instruction. 2 such addresses I should write it. 2 into 2 power of 7 into this one. Plus P, Q, R. Yes, I'm writing. Yes. So 2 power of 7 into 2 power of 7 into 2 power of 7 I can write. No? You understand this one? Opcode field, 3 address fields. Opcode field, 2 address fields. Opcode field, 1 address field. Opcode field, no address. Combination of all 3 is equal to 2 power 24. If you could be able to formulate like this, answer becomes very easy now. Answer is easy now. Answer is over now. Just substitute the values, given value, get the answer now. Whenever such encoding things are given, you should be able to write this kind of expression. Right. So now 2 power of 24 is equal to P plus. So what is given now? I'm reading now. The ISA contain 4 distinct 3 address instructions. So now I'll write it this one. This 4. So the S value given as 4. 4 into 2 power of 21. Can I write 2 power of 21? Can I write or not? Yes, Nishukumar, you can solve it. It is not compulsory you should follow this one. Any format you can solve it. A number of ways we can do it now. This is the one way I am discussing now. Okay. So now yes value, 3 address instruction, 4 are there now. The number of 1 address instructions exactly 8 times the number of 3 address instruction. So 1 address means here is a 1 address. 8 times means what? 32. So 32 into 2 power 7 I written plus. So plus the number of 2 address instructions exactly half of the number of 1 address instructions. Number of half of the 1 address means was 16. The R value 16 into 2 power of 14 I can write plus now. So now we need to calculate p value. Can you please tell me, all of you, simplify this expression, tell me what is the p value you are getting? What is the p value you are getting now? Just solve it. Try to solve this value. Yes, you can apply any kind of method. Tell me now. So the way how I am writing, number of opcodes is sum of all of them, right? So 0, no address is there, 0 address. 1 address field is there, 2 address field is there, 3 address field is there. That is the reason simply I am writing now. Yeah. What is the value? What is the value? What is the value of it? Simplify. So you are writing p equal to 2 power of 24 minus 2 power of 24 minus this 2 power of 5 we can write, right? 2 power of 5 we can write. Okay, 2 power of 5 means this becomes 2 power of 12. 2 power of 12 plus okay, just a minute. So this we are sending, right? Simplify. Anybody got the answer? Anyone got the answer? Minus 16 means what? 2 power of 4 I can write. This becomes 2 power of 18 minus. So this 2 power of 23. 2 power of 23. So p equal to something you can take common. Okay, 2 power of 2 minus 1 minus 2 power of 6 minus what is this value? 12 means 11 only, right? P equal to, simplify and tell me. This is a 4096 into something will come. Anyone got? So 8122368. 8122368. 368. This one is 0 address instruction possible. So I hope the value is correct. Yes. Now what is the conclusion I am making? Suppose any instruction, this is also possible, right? Any instruction set architecture is there. Okay, if this given as 16-bit architecture, assumption now. If this is supporting like a P and Q2 type of instruction, assumption now. There is a situation may has P can be 2 address instruction more. P can be 2 address instruction, assumption now. Q can be also 2 address instruction also can possible now. And these 2 addresses, so opcode field will be there, maybe followed by register field will be there. Let's take register I field, followed by memory field also will be there now. Here also now opcode field, 2 register field can have it like this. Assume that there are 64 general purpose registers are there, assumption now. General purpose register 64 are there. Maybe I'm taking the scenario as 128 byte memory I'm taking. 128 byte memory I'm taking. How to formulate this one? So 2 power of 16 equal to P type. P is the opcode, right? P is the opcode. What are the two address formats? One is a register, other is what? Memory. For register, how many registers are there? 64. We can write 2 power of 6. Memory is 128. 2 power of 7. I can write it. Make sense? Because it is 30 known value only. Correct. Plus, here is a Q. Q into 2 register type only. 2 power 6 into 2 power 6. So, this is the formulation when have a two types of instructions. When you have a two types of instructions. Now, it can be like, no, opcode 3 address field also can have it. 4 address field also can have it. So, out of these 2 addresses, maybe 2. One is register, one is memory. 2 memory can be, 2 register can be. When I have 3 address formats, suppose example, 3 address are there. All 3 can be memory. Some of them register, some is 2 register, 1 immediate value. Any format is there. Very simple. This you write opcode into this address field. Opcode into address field, you write it. So this format, if you are able to write it, yes, I'll get the answer. You may be giving the p value, q value, they may ask p value. Sometime pq given, they may ask total number of instructions possible. Maybe instruction length also. Various questions possible in this area. Yes, you are right, you are right, you are right. So this format is clear, huh? This format is clear, all of you. The format is clear, Nishukumar. We'll try another question. Let me take another question now. So another question I'm taking now, similar to this one. Assume that computer system in which there are 62 registers are there and total 55 instructions are available now. A computer allows only 2 address instructions where one operand can be a register and other can be a memory location. Example I told. The memory is byte addressable of 256 kilobytes in size. The minimum number of bits to encode this instruction will be dash. Try this question. Try this question. It is based on the previous scenario only. Based on the previous scenario only. Try all of you. Try all of you this question. Computer system in which there are 62 general purpose register I am taking. 62 general purpose registers are there. And total 55 instructions are available. 55 instructions are available. Okay. Now, one is memory, one is register. Memory, so no, memory byte addressable. Memory size is given now. Memory size is given 256 kilobytes. So that nothing but memory address bits. I can help you. Address bits are 1 KB 10 256. 18 bit is address, I can tell. 18 bit is address. Try. 6 plus 8. Memory itself a 18 bit address. So now instruction set architecture format I am taking. Instruction set architecture format. So this instruction set architecture format, if I take like this, okay. So as I told, opcode field we have, followed by, said na, 2 address instruction format when one operand can be a register. Let's take register RI. Other can be a memory address given now. Memory. For this memory address field, how many bits required? Because of this 256 kilobytes, 18 bits required for this area. There are 62 registers are there. How many bits required for this? 6 bits required. Am I right? 6 bits required? 6 bits required. Very nice, very nice. Now, how many such instructions are there? Total opcodes. Instruction, nothing but your opcodes only. For this 55, nothing but above 32 only. So that's definitely 6 bits required, right? 6 bits required. 12. So 6 plus 6 plus 18, right? Total will be my instruction size. This instruction size will be going to be 30-bit long. 30-bit long. Am I right? Yes, very good, very good, very good, very good, very good. Let's move to another question. Oh. Now look at this question now. Assume we have a program that takes 1 billion instruction to execute on a processor running 2 gigahertz. Suppose 40% of the instruction execute in 1 clock cycle, 35 instructions execute in 2 clock cycle, 25% instruction takes 3 clock cycle. Now, what is the execution time for the program in seconds up to 3 decimal places? He is asking. Try this question. Assume we have a program that takes 1 billion instructions are there to execute on a processor running at 2 gigahertz. Take 2 minutes time, try this question. Yes, are you trying? Are you trying, all of you? So program takes 1 billion instructions to execute on a processor running at 2 gigahertz. Suppose 40% instructions execution takes 1 clock cycle, 35 takes 2 clock cycle, 25 takes 3 clock cycle. Now we have to find out time for a program, right? Time for a program. Always do remember this one. How to calculate time for a program? 1 billion nothing but 10 power of 9. Very good. So now time for a program is nothing but number of instructions you should know. Number of instructions. You have to multiply by clock per instruction average. So clock per instruction average into time for clock. In terms of time, if you want to get it, time for clock. So this, if you understand, now one of the parameter they can ask. So here is a number program time only, direct indirect data given now. Now see, so time for a clock, how to calculate time for a clock? Time for a clock is a reciprocal to 1 by clock rate of the processor. 1 by clock rate of the processor, this also should understand now. If you know 1 clock time, if you know number of clock average per instruction, multiply to number of instruction, we will get the time for a program. Yes. First you can get the 1 instruction time average, multiply by to this one, or else you can know directly, you can also do it now. So 1.85. So 1 instruction time you can get it. So clock per instruction average. Clock per instruction average I can get it, right. Clock per instruction average. The what is given now? A program 40% instruction execution in 1 clock cycle. Okay. 40% of these instructions are taking 1 clock cycle plus 35% instruction take 2 clock cycle. 35% takes a 2 clock cycle now. Total 75% happen now. Remaining 25% takes in 3 clock cycle is given now. Total 100%, right? The value is 100% now. So this value 0.4 plus, so 0.7 plus 0.75, isn't it? This value is how much we got? 1.85 average clocks, right? Average clocks, 1.8 clocks we got, right? Clocks we got now. So now time for an instruction, if I want to take, now I'm taking, this time for one instruction, right? One instruction time. So this 1.85 into 1 clock cycle time I can take it. Okay. Or else you can put it this only directly, no problem, right? So I'll take time for a program. Time for a program equal to 1 billion. So 10 power of 9 instructions. 10 power of 9 instructions. Average clock per instruction we already got 1.85 clocks. 1 clock cycle time is reciprocal to clock rate. What is the clock rate of the processor as given? Clock rate of the processor is 2 gigahertz given, right? Yes or no? 2 gigahertz given, right? So now 1 by 2 giga. Giga means what? 10 power of minus 9 seconds I can write, isn't it? Sorry, this plus 1 into hertz will be there, right? So this is hertz, right? Okay. Now this send upside. So minus becomes, right? So minus becomes, this get cancelled. What is this value got, ma? 0.925 seconds. Yes, 0.925 seconds. Nice, nice. Up to 3 decimal places only asking. Yes, this answer. Done. Correct, correct. You're right, you're right. Very nice. So move to another question. Another interesting question. This can be MSQ question here. Theoretical question also we can expect. So especially in these areas, especially catch memory area, we can expect the theoretical questions, basically MSQ, and even memory hierarchy based also. It can be a addressing mode based questions also. So when I want to compare RISC style versus CISC style processors, okay. So even instruction pipeline cases also they can frame it. The scenario these days we are observing, giving a data multiple question, more than one question is asking. The more than one question is putting into options wise only, right? So that is the reason MSQs are possible. So we have to see which of the following statement about the properties of a RISC and CISC architecture is or not true, or not correct, he asking now. So we are talking about RISC and CISC. RISC performance advantages come from simple micro operations and deeper pipelines. CISC advantages come from compact code. So option A, statement A, option A, is it true or false? Think based on your knowledge on the RISC versus CISC. Is it true, Nishukumar? The statement is true about RISC and CISC. Yes, yes. RISC performance advantage come from simple micro operations, yes, and deeper pipeline. CISC advantage comes from compact code. The statement is true. So now you understand. RISC performance advantage come from simple micro operation. No, understand. RISC stands for reduce instructions, reduce in simple instructions. RISC style architecture, a very simple instruction, no complex instruction, very simple instruction will be there now. The deeper in pipeline, pipeline concepts can be effectively implemented in RISC style. Pipeline concept properly we can implement it in RISC style architecture, because simple instruction we can overlap that time. So basically hardware control unit design as well as the deeper pipelines, these are the main advantages under RISC style now. So when it comes to CISC style, is a compact code. Compact code, nothing but less code. Complex instructions, no? At a time, more than one activity can do it. Example, load addition. Example, if write one instruction, add, so A, B, C. This instruction under CISC style, loading A, loading B, adding on memory level, storing it memory can happen in a single instruction only. So that becomes a compact code, less code. But where the same instruction, if I want to write in a RISC style, load A, another one instruction, load B, another, add, store, maybe 4 instruction possible. That's a simple 4 instruction possible now. So this statement is going to be true. CISC variable length. So CISC variable length instruction encoding increases the decoding complexity often require multi-cycle decode stages. It is talking about CISC. In case of CISC variable length instruction, when you want encoding, it increases the decoding complexity. It requires more than one cycle for under decode. Is it true or not? Related to what? CISC style. Is it true? Yes, absolutely. Option B true. Because CISC style, CISC supports variable length. I can have 16-bit, 20-bit, 28, 32-bit, 48-bit, depends on the addressing fields. I can have instruction size, instruction format. Variable length is supporting now. Decoding takes maybe more than one cycle. So rather in case of RISC style, decoding also may take average 1 clock cycle. Here it takes more than one cycle now. This is true. So the third one, RISC pipeline typically suffer few structural hazards due to strict load store design. Think. RISC pipeline typically suffers fewer structural hazard due to strict load and store design. Is it true? Option C is true. Think on this. But this statement to answer not required to study separately. The theory concept not required to study. Existing concepts, from the existing concept, we have a clarity over that. So we are able to answer these questions. Yes, RISC pipeline. Pipeline concepts, there is some hazards in the pipeline. You might have studied hazards in the pipeline. Data hazards, control hazards, and structural hazard. There are three major type of hazards are present in instruction pipeline. Due to these hazards, the instruction pipeline performance can be affected. The speed up factor can reduce. Due to this arithmetic operations, data hazard problem can arise. Due to branching type of instructions, control hazards comes out. This will increase the pipeline time. It's directly affecting the speed up factor. Now, structural hazard, nothing but related to the hardware structure. You know the concept of pipelining, right? Fetch and store. Example, I'm taking the scenario. So to answer this one now, suppose RISC style architecture, if I take RISC style architecture. So RISC style architecture, if I take, now 5 stages I'm taking now. So 5 stages instruction pipeline if I take. So where stage names are instruction fetch, instruction decode, execute, okay, memory access, and register write back if I take now. So instruction 1, if I start fetching this one now, assume each stage taking 1 clock cycle average here now. So instruction fetch I'll do it, followed by instruction decode, then we are executing. If possible memory access I can do it, then register write back is there now. Now when you are doing instruction decode, instruction I2 I can fetch it. So instruction fetch, instruction decode write. So instruction decode I can do, execution can happen here. So memory access can happen here and register write back, right? Similarly, you understand when you are executing decoding, instruction I3 I can fetch, instruction fetch I can do. So instruction decode, execution can happen overlap. So memory access and register write back now. So now under this, when we are executing instruction I4, understand clock number 1, clock number 2, 3, 4. So instruction 4, instruction fetch, you understand now. So this is a memory access. Memory access we do it generally for what? So memory access we do for this. This is for what? Load instruction, isn't it? Load or maybe store I'm using, isn't it now? So instruction fetch also required to go to access the memory or not? Tell me. Load store instruction will go to memory and fetch also will go to memory or not? Just tell me this is correct. Loading result into memory or fetching of instruction is a memory access required or not? Yes. Required response. So now in a same clock time, you cannot access the memory. You cannot access a memory for fetch. You cannot access memory for loading, storing or fetching. These cannot be overlapped at the same time. That is hazard, structural hazard. So we have to do next cycle only. So clock cycle time will increase. That is a point only talking now, Risk pipeline typically suffer from this structural hazard for the load store instructions only. So true, the statement is true now. Yes, is it clear? Now, CISC memory to memory ALU instructions always outperform RISC load store sequence of our array computations. What is saying that? You understand now. RISC load store also understand. RISC load store also memory access required. Load store required memory access. Memory to memory reference also what memory access required. What is saying that? Under CISC architecture, memory to memory references give the good performance than load store instruction RISC style is saying that. Is it true or false? Tell me now. He is comparing load store in a RISC, memory access in CISC. This is comparing like this now. Load store and memory is comparing now. He is saying that for this array computation, memory to memory AL arithmetic operations perform better than RISC style is saying that. Is it true or false? Is it true or false? Yes, think on this statement. So now listen. So listen now. So memory to memory ALU arithmetic now. At the same time instruction, we have to load an instruction, we have to load, add and store it. Three things are happening now. When I do load or store under RISC style, only one will happen now. So most of the time you understand RISC will give the better than CISC in terms of time. Please trust me these words. RISC takes less time than what CISC. So when I'm implementing this RISC, most of the caches we use. Here also we can use a cache, but the same line of instruction. So the two memories can happen. Here only one memory will happen now. This never gives a more, but always will not give. Use the word always will not give it. Always will not give the good performance of CISC over what RISC. So this is going to be false now. So you're asking question, which of the following incorrect? Option D is the right answer. But you can think, sir, it is MSQ question now. I'm making as MSQ question. You may be thinking that MSQ question required means like produces more than one option is right. So this is not possible like this. I mean, what I'm trying to say, for MSQ question also, one option can be right. It has happened in 2025 GATE is the best example. There were many questions I made. I can say 4 to 5 questions were there, some of the session, where MSQ question also having only one option is right. So my dear students, do remember, don't forget the things. Don't expect MSQ question always having the more than one option is right. If you are keeping that into mind, so you are trying to search one more option here. Sometime very close option will be there that you are marking. So that's going to be a big mistake here now. So for this I am suggesting always you go to the instructions. So before attempting any GATE exam, real GATE exam, instruction you must read compulsory. In the instruction clearly mentions, I have seen it that paper, what is mentioned. Whenever the paper having MSQ question one option, he may giving like MSQ question like you may use one or more option may write like one or more option may write like this. Use the word. Some paper all options also write given now. Some of the paper I've seen it all options also write. Yes, that's also true. So always you select the option based on the question only, based on the concept only select it. So don't assume it. Done. So I hope this is clear now. So another interesting question, try it out. A 5-stage pipeline has instruction fetch, instruction decode, execution, memory access and write back given with one clock cycle delay, each one taking now. Bypassing hardware used. Bypassing hardware nothing but right. Operand forwarding is there now. Operand forwarding mechanism is there now. Operand forwarding mechanism is there now. Branch target is resolved at the end of the instruction decode stage only. Okay, now control hazards also resolved here by using decoding at early stage only now. So number of cycles needed to execute the code is dash. Code is given now. If I number it, instruction 1, instruction 2, instruction 3, 4, 5, 6, 7, 8. Total 8 instructions. Code is there now. Code is there. Yes, yes, this is the thing now. I will give it 3 minutes time to solve it. Tell me, solve this question, all of you. Try to attempt it. 3 minutes I am giving you. So those who are watching, try to attempt this question. Try to attempt the question. Very interesting question from related to pipeline. 2 or 3 concepts are mixed. It has a data hazards. It has a control hazards also. Data hazards are resolved by bypassing hardware, nothing but operand forwarding mechanism is allowed, and also early address detection at decode stage also there. So early detection address decode stage will produce only one penalty, right? One clock cycle time penalty will be there. Now hardware bypassing means operand forwarding, except load followed by R. So all other data dependence problem can be resolved without any penalty, and only load followed by R type instruction, load or move for R type instructions will produce the one penalty. Yes, any one of you got the answer? '96. So 96 class. Chalo, we'll try. So now time for this program only, right? Time for program with this pipeline. Time for program with this pipeline, correct or not? So instead of running like, no, it is a loop is repeating, right? Instead of running loop one by one, what I can do it, there is a pipeline time will be there for this instructions, pipeline time through pipeline, plus what you can say, extra stalls will be there, right? Extra stalls or simply stalls, we can say stalls causes Stalls causes due to data dependency problems and control dependency problems will be there. Maybe causes stalls which we do not know. Okay. First pipeline time will calculate, then stalls will look into. Listen now. So these two instructions only one time will run, correct? Huh? Here two instructions are there. Just confirm me. What I am trying to do is just confirm. Two instructions will run one by one only, because after completing 1 and 2, then my loop will start. From year to year, you understand, 1, 2, 3, 4, 5, 6 instructions are there, right? 6 instructions are there, right? But this 6 instruction, how many times will repeat? Just confirm me. Just tell me that. How many times this instruction will run? How many times this instruction will run? How to understand, sir? So move 10 into R4 is given instruction now. R4 value 10. R4 is decrementing here by 1 by 1. So 1 by 1 is decrementing nothing but it won't after starting loop only next clock only will repeat. No, next iteration will start decrementing, right? Can I say this 6 instruction will repeat 10 times? Very good. So 10 times nothing but, can I say now this becomes total 60 instructions here? Under this loop there are 60 instructions. Can I think? What is the loop purpose? When same thing if you write it, put it loop, correct? Instead of writing 61 instruction, code will be length, we are putting loop, correct? Right, 60 instructions are there, and plus 2 will be there, right? Plus 2. So here and plus 2 I am taking now, this 2. Total 62 instructions are there. 62 instructions are there. Now, as we know, under 5-stage instruction pipeline, 60 instruction if I put and run it, how many clock cycle required? We know, right? K stage instruction pipeline plus n-1 instruction, this many clocks will be there, where K is a K stages, right? K stages only. What is K stage? 5 stages plus 61. So this is 66 clock cycles required. 66 clock cycle required. Any doubt? Any doubt is there? Getting 66, any doubt is there? Yes, required response, everyone, yes. Follow me. Any doubt? 66 with the pipeline manner, 62 instruction if I run 5-stage instruction pipeline manner, will get it what 66. Very good. Now I am looking for this stalls calculation. So one thing now come to, when you are running 1 and 2, there is no stall, confirm? First and second instruction when you are running, can I get any stall? Because they are not dependent to each other, right? You are loading into R4, you are loading into R2. No dependency. Now come to the point of here, load. M of R2 value loading into R1, right? So look at 3 and move value happen, right? It is just moved only, right? It is execution time only can happen this one. Now here you understand now. Load how to happen now? Memory access have to do. Memory access operand will come. Write back I have to do R1 now. Under execution time only R1 required, correct? When you running third and fourth instruction when you running under execution stage only R1 value expecting. But under execution stage it will not produce by this third instruction, because after memory access, no, is given execution memory. After memory access only I can forward it. After execution I cannot able to forward when you are running third instruction, right? When you are running third instruction under execution time, effective address generated, end of the memory access we can forward. But this expect what? Under execution only, right? It is data dependency not resolved by operand forwarding. It is one extra penalty required. When what case is extra penalty required along with operand forwarding? Load followed by R type of instruction. R means what? Risk style instruction. Load followed by R type instruction is there, definitely cause one stall. Confirm? One stall is caused here. Clear now. Come to the point here now.
So one more now. So look at 8th instruction now. Branch not equal, then jump to what? Load. Third, you have to jump to where to jump? Loop. Third instruction, you have to jump now. When you are running branch not equal, branch instruction, I need a flag value from the subtraction, right? I need a flag value from the subtraction. So subtraction. So now you are, what is said, branch target resolved at end of the decode stage only told. End of the decode stage only you want to jump. To jump, I should know the flag value. The flag value will produce by execution stage for the subtraction. Are you understanding? When you running this result, before write back, end of the execution stage, I know R1 value, this R4 value, correct? End of the execution stage only, I know R4 value, correct or not? Tell me, just tell me. End of the execution stage only R4 value available. But this branch expecting end of the decode only. End of the decode I will not get. I have to wait for one stall. Correct? Here also. So now branch, I'll write it, I'm writing here. I'll write it here, this one. One data dependency, one stall data dependency plus one branch dependency. One branch dependent is there, right? One stall branch dependent is there. Do you agree, all of you? One branch. Now see, so first time when my R4 value is 10, that moment only here one stall required, here branch, this depends also one stall required, right? So after that, this has to repeat 10 times. Now can I say, so due to this data dependency, load is happening 10 times running, right? So 10 stalls, the load will run, load follow add will run 10 times. Now subtraction followed branch also will run 10 times. That means 10 stalls will happen. Plus one more problem also there now. Suppose example, I got information here. If R4 value not 0, we have to jump, right? Non-zero jump. When branch instruction you fetch, what is the PC value? Tell me. After fetch of the branch instruction, what is the PC value? Program counter value. Confirm me. When a branch instruction fetching is over, maybe decode time of branch instruction, what is the PC value? PC pointing to next instruction, not to this one load, right? It is not pointing to loop. Loop you have to update, right? It is pointed to what? Another instruction now. It is nothing but one instruction already fetched. You have to flush it out that instruction, isn't it? You have to flush it out that instruction. Then update the PC value, jump to what? Load instruction, isn't it? It's not thought, please. After, please do not misunderstand here. Once branch system fetching is over, it won't automatically point it to what loop. We have to update. It is pointed next instruction. Next instruction, nothing but maybe I9. I9 might have fetched it. I9 we need to flush it out. Flushing out also one stall wasted or not. So this how many times? So one time already, remaining 9 times will be wasted, isn't it? So therefore I can say, so 9 stalls will happen here now. So now total time for a program will be 66 plus 29. It is nothing but how much? 95 clocks. Yes. Am I right? Nishikumar, the value is right. You are almost close, 96. Somewhere you missed one clock, you missed it. I don't know how you calculated, but you missed by 1 clock cycle. Sorry, 95, 96, sorry. So my calculation is right, 80, 86. Correct, 95, 95 only? Confirm me. Chalo. So is it clear? Any doubt do you have? Is it clear? Do you have any doubt related to this area? Conceptual issues, anything? Any doubts are let me know. So let's move to another question now. Another interesting question, pipeline based only now. Consider 5-stage instruction pipeline P1. P1 as instruction fetch, instruction decode, execution, memory access, write back stages. Delay of these stages are given below. Instruction fetch 2 nanosecond, 2, 10, like this given now. Execution stage, EX means execution, complete all operations in 2 nanoseconds. Execution will take 2 nanoseconds for all operation except floating point operations. This floating point operation takes 10 nanoseconds under P1 now. A new design P2 is proposed where floating point is replaced by better floating point which is takes 10 times faster than the old one. What is the speed of a P2 over P1 is asking. It is again performance based question comparing two pipelines here now. Again I'll try to give 2 minutes time, try it out. 2 minutes. Try this question. Anyone tried? Anyone tried this question? So 1.25 we got. Okay, let's try. Let's try this question. P1 I'm talking. Okay, P1. So now P1, P2 pipeline you have to compare. Pipeline time cycle time how to calculate? Cycle time of pipeline will be maximum of stage, ith stage delay we have to take it, right? Pipeline plus buffer is a buffer overhead. P1 maximum stage delay is what? 10. So 10 only, 10 nanoseconds, right? Yes or no? 10 nanoseconds will take. Okay. Now they use the new design they used P2. The new design P2 is proposed where floating point is replaced by better floating point which is 10 times faster than older one is saying now. Older one compared to P1, P2 in this P2 execution stage is 10 times better for the floating point operation now. Okay. So now first P1 if it is stage delay is given now. Maximum stage delay is that is the slowest delay takes for each instruction, right? Buffer overhead is not given. Every instruction may produce this 10 nanosecond can complete like this. But when it goes to P2, this stage is becomes what? 10 times faster means what? It becomes 1 nanosecond only now. Under P2, delay for execution stage is going to be 1 nanosecond only for floating point operations. But you understand, for non-floating point operation, this will not take 1 nanosecond. It takes 2 nanosecond. Therefore, maximum of 2, 1 I have to take it. for this one, maximum of this 2. Still, so now P2 will take, your execution fetch will take, decode also take, and execution will take 2, memory is 8, write back is 2. Am I right or not? Still it will take 2 only. Why is 2, sir? 10 times faster for the floating point operation, not for the non-floating point. Non-floating point, the stage will take minimum 2 nanoseconds. So now if it is taking 2 nanoseconds, everything it has to take minimum 2 only. Maybe it told 10 faster, but the minimum it has to take 2 nanoseconds only, right? Now, so now pipeline time for this process, the P2 maximum stage delay, this value will be 8 nanosecond. Now, what is speed of factor? Speed of factor, P2 over P1. P2 over P1, we have to carefully write it, P1 by P2 you should write, not by P2 by P1. Don't misunderstand English here. So P2, we are compared to P1 now. So comparison when you do it, denominator only you should write it. 10 by 8. This value is 1.25. Yes, 1.25 is right answer for this question. Okay. Suppose by mistake if you written P2 by P1, our speed of factor always greater than 1. Do remember. Speed of factor never be less than 1. It should be more than 1 only. Because when two things, when you are comparing, both are equal only, right? When you are comparing, one of the machine or system should be higher side only, right? The performance should be higher only. So this way we should answer this question. Done. So now, so sorry, this is extra data only. You can ignore it. Okay. Now move for other question. Now, so this related to the what DMA controller, 8-bit DMA device, 8-bit DMA device operating cycle stealing mode. That is in a single transfer mode. Each DMA cycle of 6 cycle state and DMA clock rate is given 2 megahertz given now. So each DMA cycle takes 6 cycles taking now. And the cycle period is given 2 megahertz. If the processor cycle takes 2 microseconds, processor takes 2 microseconds now, then what would the DMA transfer rate they are asking? Transfer rate of the DMA. Think on this. Think on this. Try. All of you try this question. Yes, anyone got the answer? Yes, what is the answer? There is a device. Okay, we are sending to memory. Okay, by using DMA controller, right? So by using DMA controller, we are sending, correct? So 8-bit device is operating in cycle stealing mode. DMA, 8-bit DMA. 8-bit means 1 byte we are sending. 1 byte data we are sending now. Operating cycle stealing mode. 1 cycle, single cycle transfer. each DMA cycle is DMA cycle takes 6 cycles state. CPU cycle 6 cycles using now. This using 6 cycles. And DMA clock rate given. If the processor cycle takes 2 microseconds, then what would the DMA transfer rate? He asking now. Transfer rate means, so I should know 1 by time now. So 1 by time, how much is taking now? For 1 second, how much data we can able to transfer? That is becomes what? If I allow 1 by 2 transfer by the DMA to memory, how much time take if you are able to calculate? Okay. So if I allow 1 second time to transfer now, how much data you will transfer? That becomes the data transfer rate. Data transfer rate, bandwidth, all are same only now. Data transfer rate, bandwidth, all are same only now. Okay. So first here, one thing you understand now, DMA clock rate is given now. Okay. What is the DMA clock cycle time? DMA clock cycle time 1 by 2 means 0.5 microseconds comes, isn't it? But if the DMA consumes 6 cycles now, simply you can say DMA cycle time now. DMA cycle will be, so 0.5 into 6 times. This becomes 3 microseconds. Any doubt is there? 3 microseconds. Three microseconds, isn't it now? So now 3 microseconds transfer I'm releasing and CPU will take. CPU is taking how much time now? If the processor cycle takes 2 microseconds here now. Every cycles, so cycle stealing nothing but every CPU cycle. Every cycle you should ask to CPU. Am I right? Every cycle we are releasing system but we are asking, right? So now after say CPU cycle time, DMS cycle time only we are asking. Suppose I'll transfer one. Immediately I will not transfer, right? Every 3 microseconds we are not transferring. After 3 microseconds, I'll wait for CPU. I'll give you a CPU, then I'll ask it. If I get again, I'll use this one. That's nothing but, we are spending 1 by transfer, or 3 plus this take 5 microseconds takes here. So 1 byte to spend 5 CPU time plus DMA like this. 5 microseconds is spending for 1 byte now. After that again we'll take, right? Now, if I allow such 1 second time, how many bytes I can transfer? That's only DTR, right? So now DTR equal to, so 1 second into 1 byte divided by, what is the value? This value is 5 microseconds. So 5 microseconds, right? What is this value now? 1 by 5 is 2. 10 by 5, I can write it. So this I can write now, simply 1 second into byte by 5 into 10 power 1 microsecond 10 power minus 6, send upside 5 will come now. So I can do it to 10 by 5 2, 10 by 6 this is, so 2 times of 10 power of 5 bytes per second I can write it, isn't it? So therefore option B comes. Option B is the right answer for this question now. I hope everyone it is clear. So similarly, like similarly related questions you can practice DMA based one. Okay. So now, so as I told you earlier also, I have taken one session, 2-hour session I have taken on this COA, where I discuss the floating point and memory areas all. Try to watch that one. Definitely that session also going to be useful to you. Now I'll be coming up with another sessions. I'll be planning future by maybe next week. So kindly subscribe this channel so that you'll get the notification. I'll plan this core booster session, computer networks. If possible, I plan the theory of computation also. Okay. Then some other subjects also we are thinking to plan, like DBMS, other subjects also. Like we'll try maximum number of subjects to be covered as a series under GATE core booster session. So I hope this session got useful all of you. Okay. So now as I told you, so IMS we are offering 12 mock tests, all in a mock test for computer science students. Okay. Some of these already mock tests are live. Some of these mock tests are going to be live, like 10th December, 24th, 8th, and till 28th January is going to be available. Okay. So this test series is aligned with the real-time GATE exam for GATE 2026. Especially all our mentors We designed this test series. So those who are interested, you can definitely enroll. Thank you all. Thank you so much for this session.